On July 1st, 2025, a sky monitoring telescope run by the ATLAS survey program, located at Rio Hurtado in Chile, picked up a dim point of light shifting slowly among the stars. On its own, that's routine. The system catches thousands of similar objects every month. But once astronomers plugged the tracking data into their orbit-fitting software, the results kept coming back odd. They checked twice. The outcome didn't change. The eccentricity of the object's path around the Sun measured near 6, far past the value of one that marks the line between a closed, sun-bound orbit and one that escapes entirely. This wasn't some icy body loitering in the solar system's far reaches that had drifted sunward, and it wasn't a long-period comet returning after an eons-long loop. It was traveling on a trajectory so steep that only one explanation made sense. It had arrived from beyond our solar system altogether, born around a different star entirely. Scientists labeled it 3I/ATLAS, the third confirmed object of interstellar origin, following 1I/Oumuamua in 2017 and 2I/BORISOV in 2019. Oumuamua had puzzled researchers with its odd, elongated shape and its lack of a typical cometary tail, then slipped away before anyone could fully characterize it. Borisov, by contrast, acted more like a familiar comet, giving astronomers firmer footing. 3I/ATLAS stood apart from both right from the start. Its orbital eccentricity outstripped either of the earlier two by a wide margin, and it was barreling through space relative to the Sun at close to 58 kilometers per second, its so-called excess velocity. That speed isn't just a number describing motion, it hints at age. An interstellar object moving faster relative to its surroundings when it enters our system has generally spent a longer stretch of time drifting through the emptiness between stars since whatever event first flung it out of its home system. Preliminary motion-based estimates, including calculations from University of Michigan researchers, suggested an age reaching into the billions of years, a figure later sharpened considerably by chemical analysis, which we'll get to. For scale, our Sun itself is roughly 4.6 billion years old. Even cautious early estimates implied this comet had been roaming the galaxy longer than our own star has burned. There's another wrinkle to this story beyond the chemistry, though, a roughly day-and-a-half stretch in late September 2025 when a cluster of the planet's most capable telescopes happened to fall silent nearly simultaneously, right as the comet neared the Sun. What unfolded during that stretch, and which facilities stayed on watch, turns out to matter a great deal for how confidently scientists were later able to pin down this object's ancient origins. For the moment, here's the essential setup. An automated survey scope in Chile flagged a moving speck on an unremarkable morning, and within days, basic orbital math alone was enough to tell researchers this wasn't a local object. What followed was a coordinated, worldwide effort, pulling in orbiting space telescopes, mountaintop observatories across several continents, and even probes already parked at Mars, to determine exactly what this ancient wanderer was made of and what that composition might reveal about its birthplace and birth era. 3I/ATLAS was moving quickly enough that losing observation time wasn't just annoying, it meant losing data permanently, with no way to recapture it. In late September 2025, right as the comet approached its nearest point to the Sun, a run of unrelated scheduling and upkeep issues left roughly 36 hours during which several of the planet's top-tier telescopes were all effectively out of commission at once. Hubble was in the midst of realigning its gyroscopes, a procedure needed to preserve its extremely fine pointing accuracy. Webb was switching between science instruments, a thermal settling process that runs longer than a full day. Chile's Very Large Telescope was partway through cleaning its primary mirror with jets of carbon dioxide snow to strip away microscopic dust. Meanwhile, the paired Gemini telescopes in Hawaii and Chile had already been committed to other approved research programs, time slots locked in months earlier through competitive review boards that aren't easily reshuffled on short notice. The net effect. For about a day and a half, no major Western optical or infrared observatory had eyes on the comet, precisely during the period when it was expected to be most active, venting gas rapidly and revealing the most about what it was made of. In that window, the object covered well over 1 million kilometers along its path. The resulting hole in its brightness record left real ambiguity in the models scientists used to reconstruct how its ices were reacting, its outgassing rate, its spin, and how its dust versus gas output shifted during the period of strongest solar heating. That hole didn't remain unfilled for long, though. A group of elevated observatories across China, sites in Tibet, Qinghai, and Yunnan, run on scheduling and daylight cycles that don't line up with the maintenance calendars affecting Hubble, the VLT, or Gemini. Facilities, including Tibet's Ali Observatory and a station near Delingha, Qinghai, stayed locked onto the comet through the entire blackout, benefiting from the thin, dry, high-altitude air that limits atmospheric distortion. These sites logged the comet's position, brightness, and evolving coma without interruption, using GPS time-stamped, standardized data files. The observations flowed through China's National Astronomical Archive system and were made publicly accessible within about half a day of being recorded. Not through any promotional announcement, just a routine data upload. For scientists elsewhere, it turned out to be exactly the missing piece. As soon as the Western instruments resumed operation, research teams pulled the Chinese records to recalibrate their own findings. The margin of error on the comet's position shrank considerably, the gap in its brightness curve closed up, and the previously uncertain window of peak activity became fully documented. It's a quiet, largely unheralded episode, but it illustrates something real about how modern astronomy operates. The biggest instruments cluster in a handful of places, get booked far in advance, and aren't well positioned to react to sudden, fast unfolding events. A more spread out network, even one built from smaller or mid-sized telescopes, can sometimes deliver exactly what the giant instruments can't: uninterrupted watch at the moment it matters most. With the observational record patched together, attention turned to the harder question underneath it all. What exactly was this thing made of? And what did that tell researchers about where and when? It originated? The James Webb Space Telescope got its sharpest view of 3I/ATLAS in December 2025, after the comet had already swung past the Sun and was heading back outward. With its surface, ices freshly heated and actively releasing gas, the comet had built up a glowing halo of expelled material. Its coma, giving Webb's spectrometer an unusually clear target to analyze. The findings, eventually published in Nature in June 2026, revolved largely around the comet's water. Specifically, how atypical that water turned out to be. Standard water molecules pair oxygen with 2 ordinary hydrogen atoms, but some water instead incorporates deuterium, a heavier hydrogen isotope carrying an extra neutron. This heavy water shows up throughout our solar system in modest, well-charted quantities. Trace amounts in Earth's seas, slightly elevated levels in solar system comets, all tracking a consistent ratio that reflects the conditions present when our own solar system took shape some 4.6 billion years back. 3I/ATLAS didn't follow that script. Its water carried a deuterium to hydrogen ratio far exceeding what's normally seen in solar system comets, roughly 30 times higher, per the published research, and more than 40 times the level found in Earth's oceans. Scientists on the study, including NASA Goddard astrochemist Martin Cordner, put it simply: this object's makeup doesn't line up with our solar system's comets, and it doesn't line up with nearby star-forming regions either. It's a genuinely new data point. Achieving that level of deuterium enrichment in ice demands 2 fairly specific ingredients. First, the ice has to form under extremely low temperatures, since the chemistry favoring deuterium incorporation runs most efficiently far colder than conditions typical of planet-forming zones near a young star. Second, that enrichment needs a lengthy stretch of time to build up, since it accumulates gradually rather than all at once. Together, those requirements point toward an origin environment quite unlike anything close by. A frigid, comparatively metal-poor corner of the galaxy, more characteristic of an earlier era of star formation than the region that eventually produced our own sun. Carbon isotope readings taken alongside the deuterium data lined up with this same story, reinforcing the sense of an object assembled somewhere colder and, in galactic terms, considerably older than our immediate neighborhood. Separate follow-up work using the ALMA radio telescope array in Chile, carried out independently with a different instrument and technique, reached broadly, matching conclusions about the water's isotopic makeup, adding further support to Webb's results. Together, these 2 independent findings describe a comet formed at temperatures just barely above absolute zero in a region of the galaxy whose chemical signature doesn't resemble anything closer to home. This is the heart of what makes 3I/ATLAS scientifically notable. Not merely that it came from outside the solar system, which its trajectory already made obvious, but that its actual chemical fingerprint places its birthplace in conditions researchers have never directly measured before. What that meant for pinning down the object's true age, and just how far back that age might reach, is where the story becomes even more remarkable. Once scientists had nailed down 3I/ATLAS's isotopic profile, the obvious next step was figuring out an age. There's no way to get an exact birth date from this kind of data, but researchers can meaningfully narrow down the type of environment, and by extension, the general era, capable of producing an object like this. The high deuterium content signals formation under bitterly cold conditions, similar to what's found in dense interstellar clouds. Carbon isotope ratios add a second constraint, since the relative balance of carbon isotopes throughout the galaxy has shifted over cosmic history as successive generations of stars have lived, died, and seeded their surroundings with heavier elements. A body whose carbon signature looks unusually unprocessed by today's standards likely assembled from raw material predating much of that stellar enrichment. Separately from the chemistry, the comet's velocity relative to the Sun offered yet another clue. Objects freshly ejected from young star systems typically leave with relatively low speeds. Objects that have spent an extremely long stretch drifting through the galaxy, repeatedly nudged by the gravitational pull of passing stars over vast timescales, tend to build up higher relative velocities the longer they've traveled. 3I/ATLAS's velocity was high enough that some motion-based estimates place its formation many billions of years back, potentially predating our own solar system entirely. None of these approaches produces a precise figure the way a laboratory dating test might. Each functions more as a converging strand of evidence. Orbital behavior, deuterium chemistry, and carbon isotopes, all pointing the same general direction rather than any one measurement settling things on its own. Still, the overall direction is hard to dismiss. This appears to be among the oldest, possibly the oldest, individual object ever directly examined by scientists, with an estimated formation window reaching back well over half the current age of the universe. To put that in context, for the vast majority of its existence, 3I/ATLAS was already old by the time the cloud of gas that eventually became our sun even started collapsing. It had probably already spent billions of years drifting through the cold, largely empty stretches between star systems before Earth ever accreted, before oceans formed, before anything resembling life showed up here. It's important to stay careful with the phrasing. Billions of years old comes from converging indirect evidence rather than one clean, definitive reading, and researchers are still refining how to interpret those figures. Even with that caveat, though, the scientific picture that has taken shape treats 3I/ATLAS as an object whose roots trace back to a fundamentally different chapter of the galaxy's history. Colder, earlier in cosmic terms, and chemically distinct in ways current models don't fully account for. That naturally raises another question. Given how long it's been traveling, what actually happened during its brief passage through our solar neighborhood? Including its unexpectedly tight pass by Mars, 3I/ATLAS's route through the solar system didn't stop at a distant swing by the Sun. On October 3rd, 2025, its path brought it within about 0.19 astronomical units of Mars, nowhere near collision distance, but close enough that spacecraft already stationed there had a real chance to study it from a vantage point no Earth-based telescope could match. The European Space Agency's ExoMars Trace Gas Orbiter, along with a second European probe circling Mars, pointed their instruments at the passing comet. The resulting images revealed a well-formed coma with stretched-out dust streamers and intricate outflow structures, visible proof that the comet's surface was venting material actively and forcefully as sunlight warmed it further, consistent with what telescopes on Earth and in space were separately recording from much greater distances. It's worth stating clearly what this encounter didn't involve. At no point was 3I/ATLAS a threat to Earth or to nearby spacecraft. Its closest pass by our planet during the entire event stayed around 170 million miles away, an enormous distance by ordinary standards. The scientific value of the Mars flyby had nothing to do with danger. It was about perspective. Having instruments already positioned near Mars gave researchers a second angle on the comet's coma structure, adding depth to the picture being assembled from Earth-based observatories and orbiting telescopes. Combined with Webb's spectroscopic data and the round-the-clock ground coverage from observatories spread across 3 continents, the Mars orbiter imagery helped round out the full picture of how the comet's surface behaved during its closest, hottest pass by the Sun. Alongside the water and carbon isotope findings, researchers also noted unusually high ratios of carbon dioxide and carbon monoxide relative to water in the material being vented, both considerably above what's typical for solar system comets. That pattern hints that the comet's ices may have originally formed in the colder outskirts of its home system, where CO2 ice condenses more readily than water ice, and that billions of years of cosmic ray exposure during its interstellar trek may have further reshaped its surface chemistry. None of this overturns the core conclusion drawn from the deuterium and carbon isotope work. An object built somewhere fundamentally unlike our own solar system, under conditions colder and more ancient than anything previously sampled directly. But the extra data, gathered from Mars orbit, ground-based observatories, and space telescopes alike, let researchers construct a fuller, more confident account of how this ancient visitor actually behaved as sunlight touched it for the first time in billions of years. With the comet's chemistry, path, and physical activity all mapped out, the discussion naturally turns to what it all means, both for how astronomers think about the broader population of objects drifting through interstellar space, and for how the global scientific community organizes itself to study events like this. Pull back from the individual measurements, and 3I/ATLAS points to a bigger idea that may matter more than any single figure in the isotope data. The region between stars isn't just empty void, it's inhabited, sparsely but genuinely, by leftover material from other star systems, some of which formed and scattered long before our sun ever existed. Objects like Oumuamua, Borisov, and now 3I/Atelas effectively serve as physical samples of conditions that astronomical models predict, but that researchers have had almost no direct way to measure. Most knowledge about early star and planet formation comes from indirect approaches, observing distant young star systems still taking shape, or building theoretical models. An interstellar object that drifts close enough for direct study, releasing its frozen contents into a coma that instruments like Webb can analyze, offers something much rarer, an actual physical specimen rather than a distant observation or simulated approximation. Seen that way, when 3I/Atelas's ancient ice sublimated in the sun's warmth and fed material into a coma that spectrographs could examine, researchers weren't simply watching an interesting comet go by. They were sampling matter that had remained sealed away, essentially unaltered, since long before Earth formed. Material that had never been warm enough to change its original chemical signature until this passed through our solar system. This also shifts how we might think about our solar system's place within the galaxy. Rather than a closed, self-contained bubble, it behaves more like a waypoint that objects originating elsewhere occasionally pass through, on paths that, in nearly every case, will never bring them back. As of this account, 3I/Atelas has already moved past Jupiter's orbit, heading outward on a course that will send it permanently back into interstellar space. Its ices will refreeze in the cold dark between stars, its coma will dissipate, and it will keep drifting, potentially for billions more years, carrying whatever remains of its ancient chemistry toward wherever its path eventually leads. What remains, though, is the data already gathered. The isotope readings now sitting in the scientific literature, the imagery captured from Mars' orbit, and the unbroken photometric record pieced together, partly thanks to observations taken without a gap during a critical 36-hour period by observatories most people outside the field had likely never heard of before mid-2025. The tale of the September 2025 coverage gap, and the part Chinese observatories played in closing it, highlight something worth examining candidly, a real vulnerability in how the world currently keeps watch on fast-moving sky objects. The most powerful telescopes on the planet cluster in a fairly small number of locations weighted heavily toward the Americas and run largely by Western institutions. Their observing schedules are typically locked in many months ahead through competitive proposal cycles built for planned, predictable research, not for responding to sudden, urgent, fast-evolving events. When several flagship instruments happen to be down for maintenance at overlapping times, even briefly, there's often no comparable backup readily available. The September gap showed this isn't just a theoretical concern. It's a real risk that materialized during observations of one of the scientifically richest objects to pass through the solar system in a generation. China's astronomical network is built differently. Several mid-sized instruments distributed across multiple high-altitude locations, backed by automated scheduling that can redirect toward developing events, and positioned geographically to offer different observing windows than the major Western sites in Hawaii and Chile. For an object requiring constant tracking rather than occasional deep imaging, that kind of spread-out, adaptable setup proved more useful during the critical stretch than a single massive telescope sidelined for upkeep. This isn't necessarily a claim that one country's astronomical setup is flatly superior to another's. Large, concentrated instruments like Webb, Hubble, and the VLT remain essential for the deep spectroscopic work that ultimately uncovered 3I/Atelas's unusual chemistry. But the episode does suggest that a genuinely more global, redundant, and flexible observing network, one not dependent on a single region's instruments happening to be free at exactly the right time, would leave the astronomical community better equipped for the next unexpected event. Given that interstellar objects have now been spotted roughly once every few years since 2017, and given that improving survey technology will likely push that detection rate up further, this isn't a purely theoretical worry. The next object, like 3I/Atelas, could show up with even less lead time, moving even faster. Whether the global astronomical community absorbs the right lessons from this particular coverage near miss will probably become clear the next time it happens. That closing reflection on preparedness and on what this discovery suggests about our broader understanding of the cosmos wraps up this account. By the time researchers pulled together the complete picture, orbital dynamics, Webb and ALMA spectroscopy, imagery from Mars orbit, and the round-the-clock ground coverage stitched together partly through observatories in Tibet, Qinghai, and Yunnan, every method pointed to the same conclusion. 3I/Atelas is chemically, isotopically, and dynamically unlike any object previously cataloged in our solar system. Its elevated deuterium ratio, its distinctive carbon isotope signature, and its extreme orbital eccentricity all indicate an origin far removed from our own cosmic neighborhood. Not just in distance, but very likely separated from us by an enormous span of time as well, probably predating our Sun by a wide margin. No current model of star or planet formation fully accounts for every detail measured, and scientists are still working through what mix of early galaxy conditions could have produced a body with this exact chemical fingerprint. That lack of a fully tidy resolution is, in many ways, the most honest takeaway here. This wasn't a story that wrapped up with every question answered. It ended with a genuinely fresh data point, one that broadens what's known about objects drifting through interstellar space, while also making clear how much about early galactic chemistry remains only partially understood. It's also worth restating plainly what this discovery wasn't. 3I/ATLAS never posed any risk to Earth. Its nearest approach kept it around 170 million miles away throughout. The significance here has nothing to do with danger. It's about what the comet's makeup reveals about the galaxy's deep history, and about the fact that objects carrying frozen records of conditions from billions of years ago occasionally drift close enough for scientists to study directly. 3I/ATLAS has already passed beyond Jupiter's orbit, continuing outward on a course that will carry it back into interstellar space for good. Its coma will fade, its ices will refreeze, and it will resume a journey that may already span most of the universe's history, carrying whatever's left of its ancient chemistry toward wherever the galaxy's gravity ultimately steers it. What stays behind is the record. Published isotope measurements, imagery gathered from multiple observatories and spacecraft, and a nearly unbroken observational timeline that came within a critical 36-hour gap of being incomplete. A gap closed, in this case, by a cluster of high-altitude observatories that few outside astronomy had heard of before this object showed up.